All right, hello everyone. This is Derek, GSI, teaching on Mondays, covering section 12 today, which is the final section of the semester, which will be covering stated preference valuation, contingent valuation, and option value. And then at the end, we're going to dive back into hedonics, as many students have struggled with those concepts. So we want to make sure that we're giving you lots of practice with that leading up to the final exam. So what we're after today is covering those topics and thinking about, again, how to evaluate the value of goods when we don't observe goods sold in the market. So something you've probably heard me say a lot if you're in my section is, when we think about the market for clean air, this isn't something you go to the grocery store and buy. This is something you buy through the choices you make, through the recreation choices you make, through where you choose to live, so on and so forth. And so much of environmental economics is essentially learning how to determine the willingness to pay for environmental goods that are not sold in markets. So we've used hedonics in the past through these sorting questions and thinking about how much people are willing to pay, say, for air quality, and we've used defensive expenditure to at least get a lower bound, um, or under some assumptions, a lower bound of how much people are willing to pay to avoid worse air quality or worse environmental amenities, and therefore kind of backing out their willingness to pay to improve those things. So another way we do this as economists is called stated preference, which is basically when we simply ask people how much they value environmental goods. Okay, so, or any other non-market good, but since this is environmental economics class, we're going to focus on environmental goods. And then something you learned in lecture is that contingent valuation is the branch of economics, or environmental economics specifically, that studies how to measure actual preferences using stated preference style questions. So, simply asking people how much they value certain things could have downfalls. We're going to get into those a little bit later. So contingent valuation is really just a clever way of asking people questions to kind of try to back out their actual preferences. Okay. So what are their actual preferences? Well, those are the things we really care about. And why might it be problematic that we're simply just asking you how much you value certain things? Well, you could lie about it, or maybe you don't understand it, but we're going to get into those at the end of this section. So contingent valuation is subject to criticism for exactly this reason, since ultimately you are just asking people for an opinion on how much they value certain things. So they don't have to put their money where their mouth is and thus have no real strong incentive to tell the truth. So there are ways to kind of, combat this. I don't think we're going to dive into the methods of contingent valuation in this class. You could probably take an entire semester or even an entire year or 2 years of classes on contingent valuation. There's a lot of different ways that people do this, and a lot of different studies trying to kind of ground truth basic contingent valuation style questions against actual revealed preference measures, which I'll tell you what that means if you don't know what revealed preference means. But in this class, what we want you to take away from this is just to know what contingent valuation is, and that it's used to measure the value of environmental or other non-market goods. Okay, so stated preference valuation is broken into two categories. There are use values and non-use values, and and within those two types of categories, there's the following taxonomy. Okay. So let me zoom in a little bit. So use value is, as you would guess, value derived from directly enjoying or using the natural resource. Okay, so there's two types of use value. There's consumptive use, which are private benefits derived from resource extraction. So you could think farming, like when you actually use up the land and use up the nutrients in the soil to create food, or forestry when you cut down trees, or fishing or hunting or mining. Something where you're really extracting something from the ecosystem, and then you're using that to create value for yourself. And then there's non-consumptive use down here, which are generally public goods, public good benefits that do not contribute to resource depletion. So this could be something like swimming, boating, hiking, camping, viewing waterfalls, etc. So to the extent that when you go swimming, you don't ruin the water for the next person, we call this non-consumptive because your use isn't really affecting the value for the next person or excluding them from doing it. So that's why we then generally call these public goods. Um, Obviously, if you go swimming and you end up destroying a bunch of rocks that you're jumping off of or something, then you could be doing both things. Perhaps part of your swimming is non-consumptive and part of your swimming actually was kind of a consumptive use because you broke some parts of nature. So it's not cut and dry that every activity you're going to do outside is going to be one or the other of these. It could be many of these things, okay? But this is kind of what use value is. So the next thing is non-use value, which is value derived from environmental resources without physical interaction with that resource. Okay, so there's three categories of this. Let's go through these really quickly. So there's vicarious consumption value. So this is utility derived from the consumption of environmental resources by others. So for example, if you may be happy when your friends are able to visit the redwoods when they visit you in Berkeley, giving you joy even though you've been on Zoom in class all day. So if your friends come visit you and you say, hey, it would be really nice if you all went to Redwood Regional Park while I'm on Zoom, you get some joy out of being able to kind of provide that for your friends that you wouldn't have been able to provide had that resource not existed. So the next thing is bequest value. So this is utility derived from passing an environmental resource onto the next generation. So this might sound a little bit more like conservation utility. So this is utility you get, say, by preserving the Amazon rainforest to ensure that the next generations have the option to visit there. So you just want to kind of preserve nature as it stands because you think it's important that next generations are able to access those things. All right, so the final one that we've have in our taxonomy is existence value. And this is utility derived from the knowledge of the mere existence of environmental resources. So this isn't about, to kind of put this in cahoots with bequest value, this isn't about like saving it for the next generation. This is kind of more for your own utility. This is thinking about, I may never see a polar bear, but I get utility knowing they exist. Or, I may never actually visit the peak of Mount Fuji, but I like to know that it exists and I could go there if I wanted to. So that's what we think of as existence value, is just thinking, okay, I know that natural resource or environmental good exists, and that makes me happy directly. So what can go wrong with stated preference model methods? I should read stated, not state. So a few things, and I urge you to review lecture 35 for a more detailed explanation of this. This is really just to give us an overview. But the first thing we want to think about is sampling bias. So when you're doing contingent valuation or stated preference methods more generally, you are asking people questions, which will generally be done through a survey. So if, for example, what you're trying to do is learn about, say, the preferences of young people in Berkeley and their recreational habits and how much, say, they value clean water at Lake Anza, and you decide to conduct a phone survey, but you do that survey at, say, 5 a.m. when it's more likely that old people are going to answer the phone, then you're not really going to get a representative sample of students at 5 a.m. because most students are probably sleeping at 5 a.m. So you got to make sure that your sampling strategy is proper so that you're measuring the preferences of the people that you care about. So to the extent that you want to get a representative sample of all Americans, well, you better build a representative sample to measure that, and it can't just be, students or one kind of people from the northwest corners of the country, or so on and so forth, or just males or just females. You actually need to make sure that your group is representative. Um, Another way that this can go wrong is strategic bias. So you must ensure that questions are asked in a way that's such that individuals reveal their willingness to pay honestly. This is probably the biggest part of contingent evaluation. Um, and there are many, many methods for doing this. And like I said, we're not going to get into this. If this is something you are interested in, I urge you to take a class in this. I don't have a class to recommend to you, but if you are interested in this stuff, please shoot someone an email, myself included, and I can try to kind of look through the course list and see where you could build those skills for building good contingent evaluation surveys. Okay, so the next piece of that is framing bias. So the way which questions are written can influence the answer. So you could imagine I want to get the willingness to pay to protect spotted owls in Oregon. So one way I could just simply ask you, how much would you be willing to pay to save one spotted owl in the Willamette National Forest? And maybe that's fine. That's something to ask. That's going to get the valuation of that person's willingness to pay. Another way to ask that question is to say, spotted owls are the cutest animals that have ever existed. They're a key species in the Northwest forests. Without their existence, we worry about habitat collapse for other species. Did I mention they're really cute? How much would you be willing to pay to save one spotted owl in the Willamette National Forest? So you could imagine, that's an extreme example, but the way you write things down and the information you give people can all affect their valuation. So you have to be very, very careful when you write these sorts of questions that you're going to get true preferences that aren't influenced by the way you're asking the question. So these two things are like mainly CV. I'm going to say CV for contingent evaluation, and they're very, very challenging to get right. That's probably one of the main critiques of this method, is that you are essentially just asking people to value things, and there are massive biases in doing so. Okay, so the fourth thing that is kind of what can go wrong is ill-formed preferences. So people may be just completely unfamiliar with the goods you are asking them to value. So let's go back to the spotted owl example. I'm asking you to value kind of the life of one owl in the middle of the forest, maybe a forest you've never been to, maybe you don't even like going to the forest, which could affect your willingness to pay. So it could be that you're just not familiar with these sorts of situations. It's not that you're lying, you're just like maybe $20. But this isn't the same as, say, if you had to go to the marketplace and actually pay those $20 to save that owl. So this is really where kind of it's challenging. You're asking people to make decisions that they don't have to back up with actual financial transactions, and therefore it could be all kind of three of these things going on all simultaneously, and it's very unclear which way these things could bias valuation. Okay, so contingent valuation is rife with problems, but it is very important in environmental economics, as are hedonics, as are measuring willingness to pay through defensive expenditure, because we need to basically be able to value non-market goods in order to make good decisions about policy and environmental regulation. All right, so let's quickly jump into some short exercises on stated preference, and then we'll move on to option value. So I urge you to pause the video now and give these four questions a shot, and then come back and we will go through them. I'm going to dive right into them since you can pause the video. All right, so what I'm going to ask you to do here is categorize the value. It could be more than one for each of the following situations or statements. So A, Derek decided to tell his friends to visit Lake Anza and go swimming while he was teaching. This made Derek happy. Okay, let me pull this up on my iPad here so we can just write right on here. So Derek was telling his friends to go to Lake Anza while he was teaching section this morning. And this makes me happy. So what is this? Well, this is vicarious consumption value. Vicarious consumption value, and this is because my friends are consuming it. I am not, but that is making me happy. So it's his friends go to Lake Anza, makes me happy. That sounds like vicarious consumption value. All right, so now we're talking about Jim. Jim enjoyed scuba diving at the Great Barrier Reef and now donates money to make sure it exists for this generation and future generations. All right, so Jim did scuba diving. So scuba is a non-consumptive use value. And now he donates money to make sure it exists for this generation and future generations, and that could be a bequest value. Okay, and I want to note in this, if you're donating money, this could kind of, you could think of this as some sort of like defensive expenditure. You want to donate money to protect something. So that could be a lower bound of the bequest value, but the bequest value could be even larger than that. Okay. So now you enjoy a campfire while camping. So the campfire is a consumptive use value because you are burning wood. So you're actually using up the wood. And then camping, assuming you leave no trace, is a non-consumptive value. All right, cool. Sorry for the chicken scratch, but you can look into the solutions if you can't read it. So the last statement is, you feel happy knowing that there are likely as many as 70,000 species of insects in 1 acre of the Amazon rainforest. This is an existence value. Since you are happy that there are likely as many of this in 1 acre of the Amazon rainforest, you just feel happy knowing it. It's not that you actually have to go visit those things, you just know this, so it gives you utility that way. Okay. So that concludes our discussion of stated preference methods and contingent valuation. There's clearly more to learn here, and again, if this is something that interests you, please reach out to either Jim or myself or any other GSIs so we can point you in the right direction. All right, so let's move on to option value. So when we're thinking about making decisions on whether to invest in things, so much of what we've done in this class is basically compared benefits to costs and said, does this make sense? Or is this the best policy? Or just thinking through anything by kind of pitting the costs against the benefits and then deciding the best course of action. So when investments are irreversible, and by irreversible I mean think about a big piece of equipment like a sawmill or a cement factory. These things are pretty permanent. It's not like you could build this in 1 day and then dismantle it in a day and sell it. It's more likely that you're going to build this and expect to use it for the foreseeable future. Okay, so it probably could be liquidated eventually, but it isn't the same as investing that same amount of money, say, in stocks or securities or or gold or some other thing that is much more liquid, where you can just kind of go on the market and sell and buy freely. Okay, so when we're dealing with irreversible investment, it's important to think about the lifetime of benefits from that investment, since it isn't easy to quickly sell to recover costs. Okay, so when you're buying something that's quite liquid, you may still want option value. You may still want to wait to buy something that's liquid, but the benefit from waiting will be lower with something that's liquid, because if you make a mistake in the next period, you can just sell off your mistake and kind of not live with the mistake forever. Okay, so that's the basic idea. So option value captures the value of waiting to make irreversible decisions. And what are the benefits of waiting? Well, it's quite simple. When you wait, you might learn something more about the future. So you may be able to do more research. You may just learn different states of the world. You could imagine, let's use COVID for example. Let's say you were thinking about investing in a restaurant. Well, no one really saw COVID coming, but you could think, all right, well, I'm deciding to make, do I want to open a restaurant in October 2019? Well, so you do your market research, you start to think about how various things are going to work out, how you expect them to work out, and you say, okay, maybe if I spend 3 more months doing research, I can get a better handle on what might happen in the future. And then you learn, oh my goodness, there might be a pandemic coming because we have, whispers of this happening in other places around the world. And you say, okay, I've resolved some of that uncertainty related to different states of the world. And then maybe you decide, okay, the best thing to do now is to not open the restaurant after you have some more time to kind of learn things about the future. Okay, so in order to actually analyze these situations, we need to know a few things. First, we need to know how you discount the future. So this is the discount rate. And the discount rate is essentially just some way to relate um, how much you value $1 tomorrow versus $1 today, or $1 next year versus $1 this year. Okay, so it's just some way to kind of take into account the fact that if I give you $1 today, you presumably could use that dollar to make more money through the either like interest or just investing it. So $1 today should be worth more to you than $1 tomorrow, just based on that. So we need to know how you do that and how you value things and kind of your time preferences for money. And then we also need to know the probabilistic outcomes if investment is made now versus when the investment is made in the future. So what this kind of mouthful of a sentence is saying is that it could be that you make $100 with 50% probability, or $0 with 50% probability if you make the investment now. Or it might be that if you wait one period, you're going to make $50 with 90% probability and $0 with 10% probability. So you can kind of think about, okay, there's some value to waiting by resolving some of the uncertainty in the world, and we need to know kind of the probabilities uh, or the respective probabilities of outcomes in both states versus when you wait versus when you make an investment right now. Okay. So the present value benefit realized t periods in the future is written as this. So I'm going to denote it as PV sub t is the benefit at time t, which is B sub t, divided by 1 plus r, which is your discount rate, to the t, okay, to the t power. And that'll give you the benefits in time t, all in kind of period 0 or period $1, however you want to think about that. Okay, so that's just kind of allowing you to take a flow of benefits over time and make a decision about them at some time t, or at least getting them all into the same dollars. Okay, again, R is the discount rate here. So back to how we decide to invest in things. So without uncertainty and without any option value, we invest when the sum of your present value is greater than the cost. So this is saying the benefits are greater than the cost. That's all this sum is saying. With uncertainty, we invest if the expected benefits are greater than the costs. Sorry, this should be costs, not zero. Usually you could put net benefits on this side, but I just have gross benefits, so this should be greater than cost. Again, not greater than zero. Let me strike that through. And I'll fix that in the slide in the handout. And then with irreversibility and new information in the future, we invest if the expected benefits from acting now exceed the expected benefits to waiting and investing later, and presuming that those benefits are enough that they exceed the cost, so you invest at all. But you basically just choose: do I want to wait or do I want to do it right now? And then now expected net benefits need to overcome the value of waiting when we have this option value. So this is what the option value is. You can think of the option value as the value of waiting. And if we're going to make a decision right now in this period, it must be that the expected net benefits now exceed the option value plus the value that you will get from your investment in the future after you wait. Okay, so we're going to explore this in the following exercise, but this is just kind of an overview of how we set up these models. Okay, all right, so the exercise is as follows. And let me get down here on my iPad too so we can do it there. Okay, so you are considering building a solar power plant using a brand new solar technology in Nevada that will provide revenue for 2 years. Each year there's a 40% chance you'll have a good year where the project will work as intended and generate $700 million in revenues. The other 60% of the time you expect the project to have a bad year with substantial downtime as you figure out how to use the new technology, and you will lose $300 million. The project is projected to cost $150 million to install and is irreversible. You have a discount rate of 0.05. Okay, so what I first want you to do, and this is relevant to your problem set, is finish labeling this decision tree below. So again, if you want to pause the video and try and work through these problems before I go through the solutions, I think that'd be very beneficial to your learning. So just to give you a quick overview of what we are going to do, finish labeling this decision tree, then we're going to calculate present values of investing now. We're going to think about should you wait under various parameters, and then give you different parameters, asked if you should wait then. All right, so you can pause and give that a shot and then come back and I will go through this. All right, so let me fill in this decision tree. So I've given you a little bit of information in this that should be enough that we get one correct answer. So how do we want to go through this? So what we've learned in this problem is that there is a 40% chance you'll have a good year. So if we have a good year, this implies that P is equal to 0.4, which, you know, we also know that 60% of the time you'll have a bad year. So this is P equals 0.6. And if you have a good year, how much money do you make? You make 700 million. And if you have a bad year, you lose 300 million. Okay, so let's just fill this in for the other things. So this is P equals 0.4. So up here we have good year. And down here we have bad year. This is 0.6 probability. Again, if you have a bad year in year 2, you lose 300 million. If you have a good year in year 2, you get 700 million. And similarly down here, this is good year, this is bad year, and again 700 million under a good year and 300 million lost under a bad year. So that's what the decision tree should look like, which is really just using probabilities here and labeling, and then the values for year 1 and year 2. Okay. So the next thing we ask you to do is calculate the present value of benefits of investing in the solar plant today. T equals 0, and then it asks should you make this investment now. All right, so let me get a new sheet of paper. I think that'd be easier. All right, good. So we are on exercise 1B. The option value. And we want to think, okay, what are the present values of investing now? Okay, so this is going to be, if we recall our equation, well, we simply just want to take the sum from t equals 1 to 2 of the expected present value at time t of this investment, which is simply equal to 1 over 1 plus r to the 1 times the expected benefits in period 1 plus 1 over 1 plus r squared with the expected benefits in period 2. So let's just fill these in with numbers, and we can fill this in based on the decision tree. Which, yeah, we can bring it up here and then we can go back and forth. All right, so what are the expected benefits in period 1? Well, with 0.4% of the time, we get $700 million. So let's bring that down. So we have 1 over 1 plus r to the 1 power times 0.4 of the time, we get 700 million. And then 0.6 of the time, we get negative 300 million plus 0.6 times negative 300. And then plus 1 over 1 plus r squared times the same value. So 40% of the time we get 700 million. And let me bring this down to keep it a little cleaner. So we get 40% of the time we get 700 million, plus 60% of the time we lose 300 million. Okay, so this is going to be our total benefits, is just the sum of these two things. And if you plug those into a calculator, as you'll need, let me also remind you that r is equal to 0.05, so I probably should have put that in there. Let me just do that real quickly just to make sure that we get this right. This is 1 plus 0.05 to the first power, and then 1 plus 0.05 squared. If you plug this into the calculator, you get that the net present value is 185 million about. So your expected value of this investment is 185 million. It says in the setup here that it cost $150 million to install. So this implies invest. Okay, so that's the answer to that question. You should make this investment now, and what are the present value of the benefits? Okay, so next we're going to ask you what you would do if you could wait and resolve on some of this uncertainty. Add another page here. So this is 1C. So this says, suppose instead of running the plant, you can conduct research to remove most of the uncertainty in the technology at a cost of $3 million during the first year. Okay, so 3 million first year. It's really a negative 3 million because you have to spend that money. And after completing the research, there's a 99% chance that year 2 will be a good year and a 1% chance that year 2 will be a bad year. Should you wait until after the first period to make your decision, or should you build now? Okay, so we've determined what your value is if you make the decision now. So let's determine the value when you wait. So the value when you wait will again just be the sum of the expected present value of benefits time t equals 1 to 2. So what does this look like? Well, with 100% probability in the first year, we have 1 over 1 plus 0.05 to the first power times, well, what do we lose in the first year? Well, we lose 3 million through the research with 100% probability, so there's no kind of expectation in that. It's just a number, plus then 1 over 1 plus 0.05 squared, which is our discount factor based on this discount rate, will be 99% of the time we will get 700 million, plus 1% of the time we'll get negative 300. All right, so then if you plug that into your calculator, you get that that is about 622 million and 99. So this is obviously much larger than the value up here, so you'd want to wait. So this implies wait to invest. Okay, so what about 1D? 1D asks you a very similar question. You can still research the technology at a cost of $3 million during the first year, but after completing the research, there's only a 50-50 chance that the year will be good or bad. Now, should we wait or should you build it now? So what's our value here? Again, it's the sum from t equals 1 to 2 of our expected present value of benefits at those two times. So this is 1 over 1 plus our discount rate times our research cost, because that's what's happening in year 1, plus 1 over 1 plus 0.5 squared times a 50% chance we're getting 700 million plus a 50% chance we're getting negative 300 million. Which, if you plug that into your calculator, you'll get that this is 178.55. And if you compare this value to the value of making the decision now, you find that the value of waiting is less than value of investing now. So this implies invest now, don't wait. Okay, so that should get you some idea of kind of a question related to option value. I urge you to review the lecture notes on that, as there's a really nice example about shutting down a nuclear power plant in California, which is something that is actually being discussed and will happen. All right, so that concludes the option value proportion of these notes. So now we want to dive into hedonics. So a number of people, I think, struggled with this in preparing for the midterm. And it's likely you'll probably get another hedonics question on the final exam, so we wanted to make sure that everyone had a lot of practice with these style of questions and that you had resources showing you kind of a step-by-step kind of algorithm for solving these sorts of things. All right, so the question we're going to go through is actually a question from final on 2018. Let me grab a fresh sheet of paper here again. Work with both of these things. All right. So there are 5 neighborhoods and 100 identical people who all have the same utility function. So there's 100 people. Their utility function is this, so let's just jot that down. 2EQ plus 2SQ minus P, where EQ is environmental quality, SQ is school quality, and P is the price of housing. And the price of living in B through F is the number of people living there, and the price of housing in neighborhood A is always 0. So this is kind of our classic setup that we're used to in class. All right, so many of you probably have already worked through this problem in preparation for the midterm, but I've added a few parts to this that I think are useful for just thinking through these questions more rigorously and should give you some more practice with kind of the algorithm for solving these things. All right, so first and foremost, let's go through part A. All right, so since we're gonna have to fill in this table, let's do it like this. Let's just copy this down. We have a neighborhood, EQ, SQ, and then a price. So we have A, B, C, D, E, and F. We have 0, 0, 0. We're given that price is 0. We have 1, 2, 3, 4, and 5. All right, cool. So we know there's 100 people in this world, and what we want to do to solve this problem is basically just kind of look at this and say, okay, what would make this easy to solve? Well, we know what the utility is for neighborhood A because EQ is 0, SQ is 0. So if you plug that into this utility function, it's pretty obvious that UA is equal to 0. So if we're given that information, and we can posit that people are going to live in neighborhood A and neighborhood B, C, D, E, and F, then we can basically use this fact and say, okay, well, in equilibrium, it's going to be that UA is equal to UB, is equal to UC, is equal to UD, is equal to UE, is equal to UF, okay? Because that's the equilibrium condition. So if that is true, then we can basically just take each pair of these equations, setting UA equal to UB, UA equal to UC, UA equal to UD, UA equal to UE, and UA equal to UF, and solve for prices that way. Okay? But then you may ask, well, how do we know that people are living in all these places? So that's kind of a trick to these questions, is sometimes you want to look at them and just think, okay, well, where should I start? And in this case, the way I'd start is by just kind of assuming that this fact is true. You can then later prove this fact is true, but you need to kind of start somewhere in these sorting questions. So largely, step one is kind of assuming everyone lives in the cheap neighborhood, and then kind of move them around accordingly, okay? So in this case, the way I'm going to move them around is just saying, well, there's going to be at least one person living in each neighborhood. That's kind of the equilibrium I'm going to go for. And if there's at least one type of person living in each neighborhood, then it ought to be that they're indifferent between those two, and that'll kind of back out the prices. That makes sense, okay? So how do we do this? Well, let me do this for UA and UB. We know that UA is equal to 0, and this is going to be equal to UB. I'm going to put P of B in here. This is the number of people in B, or the price as it's set up. And we know that neighborhood B has EQ1 and SQ1. So if we pair that with the utility function, this is 0 equals 2 times 1 plus 2 times 1 minus PB, which gives us 0 equals 4 minus PB, which implies that PB is equal to 4. We can do a similar thing by setting UA equal to UC at PC. This simply gives us 0 is equal to 2 times 2 plus 2 times 2 minus PC, which gives us that PC is equal to 8. And then we can do UA equals UD at some price D, which equals 0. So this is the equivalent of 2 times 3 plus 2 times 3 minus PD equals 0. This implies PD is equal to 12. And then similarly, again, UA is equal to UE. Doing the math, this gives us that PE is equal to 16. And UA equals 0 equals UF implies that PF is equal to 20. Okay, so now we have candidate prices. Again, we just assumed that people live in this manner. If people did not live in UA in the final equilibrium, then this equation doesn't need to hold. It could be that just, they live in B and C, or they live in E and F, so those hold. But we're making an assumption that people live in all these places. So the second step is proving that these prices work. Is prove prices are in equilibrium. So how do we do this? Well, we basically just need to show that people live in neighborhood A, so that all these equations we just invoked work, because the fact that PB is positive and PC is positive and PD is positive implies that the prices in those places are indicative of the number of people living there. So just by solving for those, we've determined that that's the number of people living in those places. Okay, so what do we do to say that there's people left in A? Well, again, if these prices are the number of people living in these places, well, then the number of people living in A is simply going to be the total number of people minus the price in B, minus the price in C, minus the price in D, minus the price in E, and minus the price in F. And this is going to be, I'm going to call this NA because it's not the price in A. The price in A is 0, but this is number of individuals living in A. Okay. So let's just calculate this, and as long as NA is some positive number, then we've basically determined that this is an equilibrium. So this is going to look like 100 minus 4 minus 8 minus 12 minus 16 minus 20, which if you do the math here, this is equal to 40. This is NA. Okay. So if NA is equal to 40, basically what we've said is that there's, let me call N over here, there's 40 people here in the equilibrium. We've determined that the price in B is 4, and there's 4 people there. The price in C is 8, there's 8 people there. The price in D is 12, there are 12 people there. E is 16 and 16 people, and F is 20 and 20 people. These numbers being the same because that's how the prices are determined, is by how many people are living in those areas. Okay, so that's the way we approach that problem. And again, if this kind of step where you're just invoking this doesn't make sense, this is just saying if there's people with the same preferences living in 2 different neighborhoods in equilibrium, then they should definitely be getting the same utility across those 2 neighborhoods. So that's one way to approach these problems, is essentially use what you're given to back out the utilities or the prices for the other places. If instead we were given some prices and not amenities, you could back those out, but just the way we set this up was just to do prices. All right. So the next question is a more conceptual question on hedonics. So it said if one used these equilibrium prices to infer the value per unit of environmental quality in the utility function, but did not account for SQ, what would be the estimate of the willingness to pay per unit of EQ, and what is their true willingness to pay per unit of EQ? Okay, so what would this look like? Well, let's just look back at our table here. Well, an EQ of 1, they're willing to pay 4. EQ of 2, 8. 3, 12, 4, 16, and 5, 20. So each time we go up 1, we add 4. Okay, so it looks like they're willing to pay $4 per unit of EQ. So what's that? 4 per unit of EQ when ignoring SQ. And then the second part of this question is what is their true willingness to pay per unit of EQ, which you can determine directly from their utility function here. Okay, so it's just this parameter here. So true willingness to pay is equal to 2. All right, and that's, you can pull that directly out of the utility function. So this last little bit was just a add-on. This was not on the exam in 2018, but I just wanted to make a point that when we don't account for these things, we get the wrong value. But what is the right value? Well, it's the actual parameter of their utility function. All right, so we've expanded this question a little bit for the sake of section notes. So suppose SQ is equal to 5, so school quality and F is equal to 5 as it is in this table, and that all 100 people live in neighborhood F. This should say in equilibrium. So this is saying this is what we observed. This is a true equilibrium. What is the minimum value for environmental quality in F to make it so that the 100 people live there and they're making the optimal decision? Okay. So in this case, what this is saying is that UF of 100 is greater than the utility in all other neighborhoods when there's no one living there. Okay, so that's UE at 0, that's greater than UD 0, greater than UC 0, greater than UB 0 and greater than UA 0, which is equal to 0. Okay, so why did I write it this way? Well, if we just inspect this table over here, well, the utility when there's 0 people living in these places is just 2 times EQ plus 2 times SQ. So for E, it's simply 2 times 4 plus 2 times 4, which is 16. And just by quick inspection, if there's 0 people living in all these neighborhoods A through E, then E definitely dominates, strictly dominates all the other neighborhoods, okay? Besides F. We're just looking at the neighborhoods E through A right now. Okay, so I wrote it this way because E is going to give you the second highest utility compared to F. And then we need to think, okay, well, what is this? What is EQ? It's not 5 anymore. We're not allowing it to be 5. We're trying to solve for 5, given that all 100 people live in neighborhood F. All right, so we can simply use this fact. This one right here implies that if this holds, then it's also true that UF 100 is greater than all the other neighborhoods. Okay, so just a kind of quick proof. So what does this look like? Well, what is UF of 100? Well, this is equal to 2 times the environmental quality in F plus 2 times 5, which is the school quality, minus 100. And this ought to be greater than 2 times 4 plus 2 times 4. This bit is coming from these numbers here, EQ and SQ in neighborhood E, minus 0, because there's 0 people living there right now. So this is equal to UE of 0. Okay, so let's just fiddle around with this inequality to solve for EQF. So we have 2 EQF is equal to, plus 10 minus 100 is greater than 16, which if you move all this to the other side, you get 2 EQF is greater than 106, and that EQF is greater than 53. So if this happens, this implies all 100 move to neighborhood F. Okay, so if you want to verify this fact, plug this in right here, and then look what happens when you put all 100 people in there, and they should get higher utility even if just one of them decides to leave. So what it should say is that precisely this, that UF, when all 100 people are there, is greater than UE even 0. And since UE of 0 is greater than UD of 0, and UD of 0 is greater than UC of 0, and UC of 0 is greater than UB of 0, and UB of 0 is greater than UA of 0, then you've proven that if EQ is greater than 53, that no one wants to leave F and all 100 people live there. Okay? Okay. So I want to make a quick edit. I noticed this as going through the solutions that I left something in these notes that was changed in the solutions but not in this handout. So for part D, which is also was not on an exam, but I think is another style of question you should be able to answer. Suppose again that SQF is equal to 5 and EQF is equal to 5, but there are only 22 people in the economy. How will the individuals sort now? So what I screwed up on here, I left the 22 in here. Really, this should just read 10 people in the economy. Okay, so let me cross this out. I'll put a little comment here. This should read 10. Okay, so it's kind of in the way now, but whatever. Let me close it. So that should be 10. All right. So if you want to solve this for n equals 22, go for it. It's quite difficult. It'll take some time, but you can use the same sort of algorithm that I'm going to show you right now. Okay, so let me just walk you through this. So if you have trouble with these questions, I think this sort of method is helpful. It's pretty foolproof, but again, it can take a lot of time, and it's much better if you can approach these questions with a little bit of intuition first. Just kind of posit what you think might be the equilibrium and then try to prove that no one wants to move. But let me show you kind of how to start if you don't know where to start. All right, so step one, assume everyone lives in neighborhood A, or the free neighborhood. Okay, so they're getting U neighborhood of A with 10 people in that neighborhood, and they're getting 0 utility. Okay, so that's a good starting point. You just kind of assume everyone lives in the free neighborhood. Step number 2, move all high value people to highest amenity area. Okay, so in that case, what we want to do, at least in this situation, is move folks from A to F. Now you notice I said all high value. I should probably make that actually readable. I should say value. In times when you have heterogeneity and you have people with different preferences, what you want to do is take the people with the highest preference and move them to the highest amenity area. Okay, because people with the highest preferences for amenities should live in the highest amenity area in your equilibrium. In this case, we only have one type of person, so you can just think, okay, they all kind of have the highest utility or highest amenity value, so let's move everyone. Okay, so what's this going to apply? Let's move all 10 people to neighborhood F. Okay, so what does this look like? Well, if we have 10 people in neighborhood F, this is UF10. This is, again, based on the utility function, 2 times 5 plus 2 times 5 minus the price there, which is 10, which gives them a utility of 10, which is great. This is better than the utility in A, which is equal to 0. So these people all want to move. All right, so we've kind of shown all all people to F is a good move. And then step 3 is to think, does anyone want to leave F? So if they left F, where would they want to go? Well, clearly they'd want to go to E, because no one is living there, and it's the highest amenity place left over. They wouldn't want to go to D or C or B because there's still 0 people living in those places, but those places are strictly dominated in terms of amenities that they get value for. Okay, so if anyone leaves F, they're going to first go to E. So what are they going to compare? Well, currently everyone in F is getting UF10, which is 10 utility. And when they're looking across the pond, they see UE of 0, which is equal to 2 times 4 plus 2 times 4. That's from using these EQ and SQ in that utility function, minus the price when 0 people live there. That's equal to 16. So what does this tell us? Well, this implies someone wants to move to E. All right, so I'm going to show you 2 ways to approach this. Let's kind of do the brute force way first. So we had UE at 0 and UF at 10. So we know the utility there, so let's just copy these down. UF of 10 is 10. UE of 0 is 16. So let's just kind of start moving people over one by one. So this will be like UF of 9 is equal to 9, and UE 1 is equal to 15, and UF of 8 is equal to 8, and UE of 2 people there is equal to 14, and UF of 7 is equal to 7. Sorry, I did this wrong. These are all wrong. These should be going up, Remember, this is 2 times 5 plus 2 times 5 minus 9, which is equal to 11. Similarly, this goes up to 12. That goes up to 13. The counterpart to this is UE3 is equal to 13. Okay, because that's just to make sure everyone is following along. 2 times 4 times 2 times 4 minus 3, 16 minus 3 is equal to 13. Alright, so this is an important equation that we have. This is where UF of 7 is equal to UE of 3. Okay, so that tells us that we have at least a candidate equilibrium here, but what we need to make sure is that no one wants to leave these two neighborhoods. Okay, so what is the utility in these neighborhoods? Well, it is 13. And then what's the utility of moving to the next highest amenity neighborhood? Well, that would be neighborhood D with EQ and SQ of 3. So step number 4. Does anyone, or maybe that's step 4, want to leave F or E? Well, how do we do that? Basically, we want to compare this utility value of 13, so that's UF of 7 equals UE when 3 people live there, which is equal to 13, to the utility in D when there's 0 people there. Okay? Well, we can simply calculate this because we know the amenity value, we know their utility function, and we know that there's 0 people living there right now. So that is UD of 0 is equal to 2 times 3 plus 2 times 3 minus 0 is equal to 6 plus 6 minus 0 is equal to 12. And we show that UD0 is less than the utility they get from UF of 7, which is equal to the utility they get in E with 3 people. And again, since UD of 0 is greater than UC of 0, which is greater than UB of 0, greater than UA, which is equal to 0 always by assumption, then by proving this fact that UF equals U, which is UE of 3, which is this utility value of 13, is greater than this utility value at D, this implies that no one wants to move from F to D and no one wants to move from E to D. And since they don't want to move to D, and D at 0 is bigger than C at 0, why is that true? Again, D strictly dominates C when 0 people live in both these places, because both amenities are greater. So if they don't want to live in D when there's 0 people living there, then they definitely don't want to live in C when there's 0 people living there, or B, or A, okay? So there we've shown the equilibrium is price in F is equal to 7, and the price in E is equal to 3. And the prices are 0 everywhere else. Okay, so let me go back to step 3 and show you a different way to do this. Okay, so one way to approach this is to kind of use this table. Sorry, I screwed that up on the first time around. Let me just go through this one more time to make sure everyone understands. You start with all 10 people in F, then you have 0 people in E, you make that comparison. Then you're going to move one of these people from F into E, so you end up with this comparison. So this is 2 times 5, 2 times 5 minus 9 is 11. So this side is increasing, this F side is increasing, this E side is decreasing because people are moving into E and away from F. So it's going 10 to 11 to 12 to 13 as people leave, and 16 to 15 to 14 to 13 as people arrive in E. So you can use a table argument like this and then try and find some like inflection point to where people stop moving, and then you kind of know what's going on. But really, once you get this fact that someone wants to move to E, which is what this is showing you, because the utility when there's 0 people there is 16, and the utility when all 10 people are in F is 10. That shows you that someone wants to move from F to E. And what you can do there, let me add a page, is you say, okay, if UF of 10 is equal to 10, and this is less than UE of 0, which is equal to 16, this implies at least one person goes from F to E, which tells us what? Well, we know in equilibrium that UF, the price of F, is going to be equal to UE, the price of E. We don't know these numbers because we have to solve for them. But what else do we know? Well, we know that N is equal to 10. There's 10 people in this economy. It says 22 down here, but this should really read 10. I just want to remind everyone of that. So what does this tell us about the relationship between PE and PF? Well, let's make an assumption. Assume people only live in E and F. So this is a guess. This is not a fact. We don't know this yet. I know I've shown you it previously, but when we're solving it this way, we don't know this fact. But what does this tell us? Well, we know that N equals 10 is going to be equal to PF plus PE. Okay, so this is the number of people living in F, this is the number of people living in E, and since we're assuming people only live in these two places, that has to equal the full universe of people. So this allows us to write an equation where we can relate PF and PE and actually use this fact to solve for things. Okay, so how do we do this? Well, this tells us that PF is equal to 10 minus PE. We can use this equation inside this equation in order to solve for one of the prices. Okay, so what does this look like? Well, we have UF of PF. Well, what is this equal to? This is UF of 10 minus PE by plugging that in there. And what does that have to equal? In equilibrium, if people live in these two neighborhoods, that has to equal UE of the price at E. Okay? So then we can use these two expressions to solve for PE. Well, what is UF of 10 minus PE? Well, this is 2 times 5 plus 2 times 5 minus 10 minus PE. And what does the right-hand side of this equation look like? Well, this is 2 times 4 plus 2 times 4 minus 10 minus PE. Sorry, not 10 minus PE, just minus PE. And if we chug away at this, this is 20 minus 10 minus PE equals 16 minus PE. So this is 20 minus 10 plus PE, just carrying that negative through, equals 16 minus PE. This is 10 minus 16 is equal to negative 2 PE. And we get that negative 6 is equal to negative 2 PE, or that PE is equal to 3. Okay, so now we solve for PE. We can plug this back into this equation up here to get PF. Well, PF is simply 10 minus PE, which is equal to 10 minus 3, which is equal to 7. Okay, so you can do it this way as well. Sometimes it's actually much easier. You could imagine if we had to move a lot of people from F to E in this kind of table way, indicated right here. You'd be there kind of all day moving people one by one. By doing it this way and invoking kind of this fact, you can solve for things a little bit more algebraically. So there's two different ways to approach these questions, or at least that step of the question. Whether you do step 3 with the table type method or this more algebraic method, you'll get to the same place. And then remember, here you assumed that people only live in these two neighborhoods. So step 4 still needs to happen in both cases, because you need to check, do they want to leave? Okay, so again, we assume that they only live in these two places. When we come to step 4, we need to prove that no one wants to leave these two places. And by proving that, we've basically satisfied our assumption, and therefore the prices that we get from these two equations hold. All right, so that's it's actually it's not necessarily, I don't want to say easy, but that's a kind of not a very long problem to solve. If you really want to try it with 22 people, you can. I'm happy to provide you the answer. Just send me an email. I haven't written up a solution for that, but I can just give you the answers if you'd like. But what you'll find is it gets more complicated because you're going to have people living in multiple neighborhoods, F, E, and D, at least. So it gets a little bit more complicated when you go to this algebraic step, because here we simply could assume people only live in E and F and use this fact, and then we basically have one equation with one unknown. If you do it another way, and let's just go down here and just say assume people live in D, E, and F, then what are you given? Well, let's do this for n equals 22. I'm not actually going to go through this. I'm just going to set up the equations. Well, you know that n is equal to PD plus PE plus PF. What else do you know? Well, you know that UD is equal UD at price D is equal to UE at price E is equal to UF at price F. So here you have basically one well, how many equations do you need here? Well, you have three unknowns, so you need at least three equations. What are the three equations we could use? Well, you have this one, and then you have UD PD is equal to UE PE, and then so if this is 1, that's 2, and 3 could be UE PE is equal to UF PF. All right, so now you have kind of three equations and three unknowns. You actually have a fourth equation in here, so you could kind of simplify things a little bit as you did previously, but you just have a larger system of equations to solve. So it's not necessarily like harder, it's just you're going to have to use more algebra to do this. So when you get into these questions where people are sorting across 2 or 3 or 4 neighborhoods, it can get pretty cumbersome, the math. But I just wanted to kind of show you the approach to these questions if you really don't know where to start or you don't know where to guess. So yeah, and just to reiterate, this is one way to approach these questions. It's by no means the only way. So if you have something that works for you, I suggest go with that. If you have questions about the way you approach these problems and whether it's right or wrong to do it like that, I'm happy to provide feedback. But I do get the sense that one of the frustrations with hedonics is that there are multiple ways to approach these problems. They should all get you to, unique equilibrium or equilibria. But what is happening in a lot of these problems is you just have to start somewhere and then start thinking, do people want to move? All right, so if you can't figure out where to start, I've showed you one way, but you can really start by putting people anywhere and then just start moving them around. So that concludes section number 12. So we'll go through this obviously on YouTube and then in class. So if you have any questions, please bring them to your GSI during section, and we look forward to fielding your questions. Thank you so much to everyone for dealing with this semester. It's been a massive learning experience for all of us. I have no idea what the fall is going to look like, but I do wish you all the best. We're going to find time to schedule a midterm or a final review session, so this won't be the last time you're hearing from the GSIs, but this will kind of be the last kind of classroom element to this session. So again, thanks everyone for putting up with the Zoom. I'm sure everyone's lives are in different levels of disarray, so I hope you all stay safe out there. And our goal is to not stress you out and to help you, get through this class. So if you do have questions, please reach out to us. All right, everyone, stay safe out there. Bye bye.